My name is Mike, and I'm the main system administrator for Astra. And what is Astra? Astra is, you might have seen some news about the new ARM64 systems that are, and this is a new one that we just got in, and it actually made the top 500. We're using it to evaluate alternative processors. We want to know that if our ARM processors can work as well as x86 and PowerPC. We want to learn about the ARM64 hardware. We want to learn about the firmware. We want to know about the support infrastructure, and also we want to evaluate the software environment. And we want to do this all at HPC large-scale systems. We got in Astra in the fall. We got it in about a month before SC18. So we basically slapped the system together and then ran it, initial evaluation to see where we were. And then we've got back, you'll see we ended up at 203 on the top 500 list for high performance LinPack. And then more important to us, we ended up number 36 on the high performance conjugate gradient test. And that one maps more along the lines of the kind of loads that we run at Sandia. And so that was a pleasant surprise. So what is Astra? Astra is basically 2,592 nodes, and they're arranged 4 nodes per chassis. You'll see we have up in the upper left-hand corner, you'll see we have 2 10 gig Ethernet ports courtesy of Mellanox. We also have 2 sockets, 28 cores per socket, and 4 nodes per chassis, like I said. There's 9 units that are called scalable units, and what they do is we arrange 4 racks per scalable unit, and then there's 72 nodes per rack. We arranged them so you'll have 3 InfiniBand switches set up in a fat tree per rack, and they're arranged in a fat tree, so there's 24 nodes per switch going to for connectivity, and then 12 links going up to the next layer of switches. And then we also have 2 Ethernet switches as well. So each one of these nodes is arranged in a front to back order. We have a socket in front, socket in the back, 28 cores per socket, and then in the back end you'll see a Mellanox EDR InfiniBand connector. Those are arranged in what we call socket direct, and so you'll have each socket gets 8 lines to the EDR connector, and that allows us to get better connectivity. And I'll explain that a little bit further down the road here. So Astra, I'm sorry.
Is that 145,000 cores?
Yeah, it's right in there. Astra is part of the Vanguard program, and I'm going to explain a little bit what Vanguard is. Vanguard is a test bed basically for us to evaluate at larger scale technologies that if we decide we like them, we'll move them into advanced technology and commodity technology HPC systems. The advanced technology systems represent specialized HPC hardware. Commodity systems represent a collection of off-the-shelf components. So Vanguard fits between what we call the smaller systems that we evaluate as test beds and the large systems. So we basically are able to take what we would evaluate on a test bed at small scale, scale it up, look at it, and say, hey, is this viable for a big leadership class system for the DOE? In the case of Astra, Astra is the first system in Vanguard, and this is kind of explaining a little bit about how Astra came to be. We basically got Astra in, and we got a brand new building to go with it with a brand new cooling system, and that was all done at the same time. So we were constructing Astra while we're constructing the building that contains a cooling system that's exotic, and so we were all in hard hats for a little bit while we were working on the system. I started with Astra as part of the testbed program. So we evaluated, the first system we got in with the ARM was Hammer. Hammer was a small testbed system. I started with Sullivan. It was a Thunder X1 system. And then we moved into the next generation was a Thunder X2 system, Meyer. And Meyer, we had several generations of hardware. We were able to evaluate firmware and hardware for each system. We started with A0 Silicon Thunder X2, and then moved to A1, to B0 and B1. And each generation, we would get in new features. For instance, when we started with the BIOS and BMC, we would get metrics that didn't record anything, basically. And so we'd go out there to get fan speeds or cooling temperatures of the silicon or whatever, and those systems would the system would report back null numbers, basically. And then each generation they'd add new features to it, and we'd evaluate it and say this works, this doesn't work, and it was kind of a nice feedback loop between us, HPE, Marvell with Cavium, and Mellanox. For instance, Mellanox, when we first got the first generation of Meyer system in, it was a common EDR network, and that changed, and I'll explain what that change was as we went along. And then once we got to a certain point, then we said, okay, let's go evaluate this at at a bigger scale, because we knew the test beds were going to give us effects that when we scaled up, that would change things a little bit. For instance, we'd have cooling systems that were different. The fabric would look different at scale, and MPI even MPI communications would change. So hence we ordered Vanguard, and we've been working through some kinks on that as we go too. So Vanguard is an effort of different things. For instance, we've got hardware we're working with firmware, we're working with cooling systems, and in this case we're working with the software. So software environment, we're looking at multi-physics production modes, we're looking at optimizing performance, for even simple things like memcopy, and things that you normally take for granted on x86 systems are a little different on ARM. For instance, even the topology of the processors is different. So we're learning as we go. Part of the Vanguard system is advanced technology software environment. We call it ATSE. And the goals for ATSE are software support for our DOE missions. We're looking, in the case of Astra, we're looking to support ARM64, and we're looking to support the ARM64 environment with compilers. We're evaluating containers, and then we're also evaluating open source versions for public users. ATSE is a merge of two different philosophies. For instance, on the left side, you'll see we have vendor software, TOS, and Red Hat, licensed software, vendor software. And on the other side, we're bringing in open source. For instance, we're bringing our ATSE packages in. Those are considered to be open source for the most part. We're working with OpenHPC. And then some vendor software that is open. And then we're using Open Build Server and merging them together to make a total package that we can use for the NSSA, the national, the DOE and the NSA. And so the ATSE programming environment, we've got containers, we've got native installs, we've got virtual machines, and that's all layered on top of the vendor stack, or you can, another alternative would be the DOE stack that we use at Livermore and Lannel and Sandia, which is called TOS, Trilab stack, and then OpenStack as well, for instance, OpenSUSE or CentOS. And then we're able to apply them in different ways to get to the Vanguard hardware and get our mission accomplished. So we have different operations that we're doing. For instance, right now we've been working for several months with HPE, which is our one of our partners, and we're working with them to build out a brand new environment for building out HPC systems called HPCM that provisions, and it also provides monitoring. And then we're also working with applications, and we're doing things with, again, with HPE on their MPI. Alternatively, we're using OpenMPI, and we're putting that stack on top of the Mellanox OFED stack. And then we've got our compilers, and everything's running nicely, neatly on top of Red Hat right now. So when you look, if you are on Astra and you log in, you'll see we have different packages listed. You can, for instance, get your common OpenBlaz or whatever. We got different like SPAC stacks and so on and so forth. We've got Singularity, different modules that you can load up. And we're evaluating as we go. We've been working with vendors as we find things that don't work, like for instance, software shortcomings, we're engaging with our open source community partners. We're also engaging with Red Hat. We're engaging with the HPE. And the goal is to get continual improvement in performance, for instance, on MPI and with software installations. We've been working with Livermore to apply the SPAC stacks to ARM on both Meyer and Astra, which is Meyer is the test bed. And so far we've had good luck on all the fronts with that. This kind of gives an overview of the communications. For instance, right now, the number of cores, there's a problem with the way the new systems are going. We're getting more cores versus memory available to each socket. So what happens is you get less memory per core, and therefore when you do communications for RDMA, you have less memory available for IB short messages. If you do things like zero copy, they're a two-step operation. In a normal machine, you'll have one socket connected to the HCA, and I was mentioning earlier we made some adjustments to that. In this case, we'll have two sockets connected to the HCA. And what we did was we took 8 lanes for one socket, 8 lanes for the other. So the improvements, new and neck interfaces, increase our memory bandwidth and reduce memory consumption. We have Sharp available as a hardware collective, where the HCA can perform simple MPI operations like all reduce and barrier without moving the data to onboard memory. And that's all executed by socket direct. And we worked with Red Hat, and we also worked with Mellanox to come up with that. Early on, we found we were very near the theoretic limit of 100 gigabits per second EDR by using socket direct. And I think we were the first large-scale implementation of UCX, which is the new API that Mellanox and others came up with for large-scale HPC networks. This kind of shows that. We were running about 96 gigabits per second right out the gate once we implemented that. So, like I said, you have one socket with 8 lanes, and another socket with 8 lanes, and they're directly connected to the HCA, and so we're getting really good performance. Next thing I wanted to bring up was we've got hardware collectives. I'm going to be talking a little bit about that in the next few weeks too. It's easy to implement. We found that out. We are running with a factory network for our HPC RDMA network, and that was supported automatically by default by Sharp. Alternatively, you can also do Dragonfly networks. Setting it up was just notifying the subnet manager by a configuration setting that Sharp was available and that we wanted to use it. It shows up kind of interesting. One thing we found out was it shows up at port 37 with EDR. There's only 36 ports on a switch. So it said, oh, let's make port 37 the Sharp network. Sharp config file, we also notified it was an up-down factory network. And then initialization consisted of just using Mellanox applied scripts to install the aggregation manager daemon, which goes on the subnet manager. It was brought up earlier in one of the talks. I didn't know if anybody caught that. And then each compute node has a Sharp daemon running on each compute node to be part of the network as well. So this is one of the Sharp, we ran at Sharp 1,024 nodes, and we, after setting it up, you'll notice there's quite a performance difference. There is a limitation on Sharp for the HCAs. There's 4,096 bytes. And I set it for 4,096 bytes, so anything over 4,096 bytes gets transited to the compute node as a normal operation. But for all reduce and barrier, if you're staying 4,096 bytes or less, you get a huge performance improvement. And what that happens is, if I send 4, 16, 64, or 256 bytes, for instance, on an all reduce, it actually gets computed in the network HCA, doesn't get transited to the compute node memory and operated by the CPU. So it's getting it gets worked on in the NIC, and therefore, because there's not a lot of latency and a lot of from transiting through the system, and it doesn't have to be worked on by the CPU, you get a big performance improvement. We were very happy when we saw that example, and there's a few others like that.
That picture begs the question about that.
What's that? Go back.
What's the weird data point with Sharp?
That one weird one, we were running the IMB benchmark. We're not quite sure what that is exactly yet. We're going to run some more tests and see what that looks like. So the IMB benchmark, it works its way up in from 64 to 256 and so on and so forth. So we're going to try to get some more fidelity out of it and some more tests. But even with that weird spike, you can see there's a big difference. So another enhancement was that we liked on the fabric was the UCX API, and I think we're the first, like I said, the first implementation at large scale, and we were really impressed. First of all, because right out of the box, it worked really well, and it was stable. It was easy to implement with newer generations of OpenMPI, and I kind of drew a little diagram of how that works. So OpenMPI set up with the Unified Communication Protocol API, which is part of UCX, and then that calls the Unified Communications Transport Protocol API. So UCT, or Unified Communications Transport, is just a little bit of an abstraction on verbs. And what it does is that it sets up your connectivity between your source and destination when you're doing a transit. And then you'll see you can have multiple UCTs, transports, running on the same UCP. And the whole idea is if this is congested or whatever, it can go to a different UCT and get to the same destination. And then the other cool thing about UCP is it allows it to look a little like MPI. When you start looking at the API, it looks like MPI. Cooling system on Astra is also one of the reasons I brought the building up in there. Was we were the second large-scale system to implement radiative cooling to aid in the cooling system. We have something called a thermosiphon on top of the building, and the thermosiphon is an additive feature to the cooling system in that it, when it's cool outside, for instance, it won't need to draw air and water from other cooling sources within Sandia. Valve opens and closes when if the thermosiphon's not efficient, it'll bring more water in from Sandia's cooling towers. And if it's really efficient, like the other day, it was really nice and cold in Albuquerque, so the valve opened up all the way into the thermosiphon, and we weren't drawing any water from the Sandia cooling towers. The cooling system is designed on Astra so that up to three racks of compute nodes is cooled on the system per what they call an MCS. The MCSs are the short blocked off racks here. You'll see what they'll do is the MCS pressures the front of the rack, and then the air flows over the water cooling to the back of the rack. So keeps things nice and under control for the temperatures. Early results from Astra. We had quite a few improvements compared to Haswell. These were measurements that we got from different tests. For instance, linear solvers were at 1.87 times improvement. So Astra, this is our numbers for our HPL run. We were running at 1.529 petaflops on the submitted run for supercomputing, and we're expecting to improve on these. And then on HPCG, we were running at 66.942 for our run for supercomputing. We're expecting to improve on it because, like I said, we slapped the system together in a big hurry. Cooling system wasn't all up to speed yet, and we didn't have the processors all tweaked out yet. And like I said, we're making improvements in the software environment, so that's going to show up in better numbers. And also, we're making some adjustments to the even the memory bandwidth. We're modifying the compute nodes on scale to do better numbers. New efforts coming up. We're working on containers. We're talking about doing Charlie Cloud. We're talking about, we're working with Singularity, a few other things. An effort I'm leading is BGFS. We're evaluating that with ARM. We're also, like I said, we're improving MPI support, and that'll hopefully give us better numbers. And then we're doing OS optimizations for different things like getting better response from the fabric and better response from the latency on the memory bandwidth and things like that too. So, and also we're working on things like getting metrics back from the Encore on the processors and things like that. We're going to continue to optimize software packages. We're going to keep building our frameworks for building out the system for software, and we're also working on, like I said, package container. VM images will come a little later on. We're hoping to add to the OpenHPC community with new items and that we get back. We're exploring SPAC. SPAC is a great way to package we found it's really great for packaging our software and building it out. So we're working with that. And anybody have any questions? Okay.
So you showed that you're using both Koji and Open Build Service.
Mm-hmm.
Talk a little bit about your experiences with getting those set up. Have you used AWS or the free one,
I haven't been really working with the software builds that much, other than a little bit with the Open Build Service stuff. So I'm not quite sure what the other guys have gotten out of that yet. So I can take that offline and find out. What's that?
Is it a paid OBS or free?
It's a free one. Yeah.
So in your user community, with that application, is something that's been well optimized for x86, what kind of effort is it to well optimize for ARM?
Okay, so for instance, some things that we've been running into, and it's kind of funny because we've got a lot of people that have a lot of experience with Intel processors and PowerPCs, for instance. The topology of the processors is completely different. So we're looking at simple things like one core will not be nearby another core, for instance, when you're doing memory NUMA setups and stuff like that. So that's a little different. And then other things, like I said, we're using Socket Direct. That's a new feature. And that it adds more. The people that the old rules were set this way, there's new rules to everything. So.
Is it like, 2 weeks of effort, or is it?
We found it's months and experiments, lots of experiments.
How much insight did either Cavium or HP have about those kinds of things? Were they learning with you?
They're learning with us. Everything that we're working on is trial and error experiment. We're learning even simple things like cooling, software topology, like I said. It's all a new experience. And some of it's just because we're scaling the system up from a test bed.
Any particular compiler that has been simpler
So we've been working with the new compilers and the ARM compilers. I've been using mostly the new compilers and had good luck with those.
How's your operations per watt relative to?
Yeah, I'd have to get the numbers out. I had to figure the numbers out. I know what they are, but I'm not. I know raw numbers, but I'd have to figure them out. I could get that for you offline.
Do you have a wild guess in terms of percent difference?
Not really. I think they're right about the same, but compared to an Intel processor, we didn't really get any. We didn't really see a difference in getting low energy usage out of the ARM system. That wasn't really a goal either, though. So.
Now, as you connect one HPA to two sockets, is there a dramatic improvement?
Yeah, so normally, and I kind of went through that a little fast. So normally what happens is you have one socket, and that's connected to the HCA, and then there's another socket that has to traverse, and that is a bottleneck, and we noticed it right away. It was pretty, once we implemented socket direct, that was a big difference. And initially with Meyer, I think that was our second generation board. It was wired into the board, and then Red Hat supplied a kernel. And then he said here, and then Mellanox supplied some work into developing some of the parts too. And then what we did was we ended up patching the kernel. So there was a quirks.c patch in the kernel that we would implement. Instead of seeing just one port, which in our case was MLX50, you'd see two ports, MLX50 and MLX5-3. And really they're the same HCA, but it appears different lid number and different connection as far as the person that's writing verbs code or whatever would see. So. Any other questions? Oh, okay.
I'm curious, did you guys engineer the cooling yourself?
So again, collaborative effort. It was engineered by HPE, and then we've been working with them on it. For instance, we're giving them feedback on rack temperatures, pressures, and then there's some adjustments that are made to the cooling system as far as pressure. Well, there's two pieces to it, I guess. The thermosiphon was engineered by us, and then the part that they implemented on Astra was engineered by them, but we're taking and providing feedback on it. And it's just simple things like fan speeds on the chassis that are containing the nodes. We started out with it going from 60% fan speed to 100% fan speed, and then we found out that wasn't right, so we're down to 80% fan speed as a top. And what that does is it keeps pressure more even across the racks.
So looking at R&D, we see other vendors with SAP coming up, et cetera. What's your kind of view of the future of R&D?
We're having good luck with it. There's, like I said, it's a learning experience, so we haven't gotten everything tweaked out yet, but we're getting good numbers. And Astra's a big system, but the fact that we got on the top 500 was a really good sign right away without doing any tweaks. And like I said, we're expecting quite an improvement of those numbers. And so, like I said, it wasn't that we expected we're going to get, everybody always thinks ARM, your cell phone, small processors, low heat. That's not what we were expecting, and we didn't get that. What we did get was an alternative processor, and combined with the other technologies, we're getting good results.